Hi, my name is Greg Folletto. I'm a Los Angeles area physics, math, SAT, and ACT tutor. Today I'm doing a physics problem. I'm going over how to find the capacitance of a cylindrical capacitor. So here you can see the capacitor. It has an inner shell of radius A, an outer shell of radius B, and it has a length of L, and we're going to get its capacitance. So we're going to do that in 3 steps. First, we're going to find E, the electric field between the 2 plates. And we're going to do that by using Gauss's law, which is always the easiest way to find electric fields in problems where it applies. Second, we're going to use the electric field E to find V, the potential difference between the 2 shells. And finally, we're going to find the capacitance using the definition of capacitance, C equals Q over V. Okay, cool. So first we're going to find E using Gauss's law. Gauss's law is the integral of E dA equals Q over epsilon naught. Cool. Now, to get the integral of E dA in this case, with this cylindrical shell at an arbitrary radius, R, how you would do that is you would just find the this side surface area of that cylindrical shell of radius r, which would be 2 pi r, which is the circumference of that little ring shell, times L, which is the length of that ring shell, and that gives you that surface area. Okay, and that's your integral, and you just multiply that by E. So that's your left side of the equation, and that is equal to Q over epsilon naught. So to get E, we just solve for E in this equation, and we get E between the 2 shells is equal to Q over 2 pi r L epsilon naught. So that's for radius between A and B. And now I'm going to actually rewrite this really quick using, in physics we say charge per unit length is equal to lambda, and lambda is equal to Q over L, which makes sense, charge per unit length. So we have Q over L in this equation, so I'm going to replace that with lambda for reasons that will come up later. So E equals lambda over 2 pi r epsilon naught. Cool. So that's step 1. Okay. Step 2 is to use this expression to find V, the potential difference between the 2 shells. We know that V always equals the integral of dV, but dV equals negative E dr, because dV dr equals negative E. That's just a standard electromagnetics equation. So V equals negative the integral of E dr, and with respect to radius we're integrating from A to B. Cool. So substituting the expression we just solved for, it's negative the integral from A to B of lambda over 2 pi r epsilon naught dr. Okay, now in this next step I'm going to take out all the constants I can, and I'm going to cancel out that negative by taking that away and switching the limits of integration. So we get lambda over 2 pi epsilon naught times the integral from B to A of 1 over r dr. Cool. So the integral of 1 over r is natural log. So we get that V equals lambda over 2 pi epsilon naught times the natural log of A minus the natural log of B. And because of the rules of logarithms, we can write that as lambda over 2 pi epsilon naught times the natural log of A over B. And that is our expression for V, the potential difference between the inner cylindrical shell and the outer cylindrical shell. Cool. Okay, so that is step 2. Now finally, we're going to go to step 3, which is to find the actual capacitance using the equation C equals Q over V. I'm going to go back to this lambda equals Q over L equation, and when we plug in Q, I'm actually instead going to plug in Q equals lambda times L. Okay, and for V I'm going to plug in the expression that we just got. So C is equal to lambda times L divided by lambda over 2 pi epsilon naught times the natural log of A over B. Alright, so these lambdas cancel, which is why I've been messing around with them this whole time. Now we have a denominator and a denominator, so this gets put up to the numerator. And so our final answer is the capacitance is equal to 2 pi L epsilon naught divided by the natural log of A over B. Cool. So that is the capacitance of a cylindrical capacitor. It looks like this. And so just kind of recapping how we did that. Remember, first we found E using Gauss's law. We took that integral, it was just 2 pi r L. At any given r, that would be the integral of dA. We just multiplied that by E. We solved for E. Instead of Q over L, we used lambda, because it ended up canceling out later, was why we did that. Next, we used the electric field we found to find V. So we integrated negative E dr, using that E expression that we just found. And we got the V was lambda over 2 pi epsilon naught times the natural log of A over B. Finally, we used that expression in the definition of capacitance, C equals Q over V. And for Q we plugged in lambda times L because it canceled with the other lambda, and we got the capacitance was 2 pi L epsilon naught over the natural log of A over B. So I hope that was helpful. If you have any questions, you can ask them in the comments below. This same approach is how you could get the capacitance of like also a spherical capacitor, for example. It's the exact same idea. So yeah, let me know if you have any questions. For more videos like these on how to solve math and physics problems, go to my YouTube channel or my website at latutor.net. On my website you'll also find lots of helpful information about the SAT and ACT, study tips, all kinds of good stuff like that. So thank you so much for watching, and I will see you guys again next time.